Welcome to our Engineers Newsletter Live program. Today we'll cover ice storage system design and application. I'm Jeannie Harshaw from Trane System Engineering Department, and I'll be your host today. Before we dive into today's broadcast, let's cover some of the housekeeping. Through our association with the American Institute of Architects, credit towards continuing education can be earned for viewing today's broadcast. If you are an AIA member, make sure you provide your member number to your local host before leaving today's session. In several states, this certification can also be applied to engineers' continuing education requirements, so please check your state's rules to see if this might apply to you. We all realize that electrical supply chain of the future will incorporate a higher percentage of renewable energy, like wind and photovoltaic solar. While clean and unlimited, these forms of energy are intermittent in nature and will require some form of energy storage to meet their potential. Thermal storage is not only an easy way to store energy, but it is reemerging as a valuable energy and energy cost-saving technology for building owners. Our goal today is to provide you with a clear understanding of ice storage and a higher level of comfort with design and application. We'll start with providing a better understanding of the resurgence of ice storage and cover a bit of theory. We'll quickly move into qualifying a project, then discuss the design steps and move into application and controls. Along the way, we'll cover some myths and common stumbling blocks, and finally, we'll summarize the economics of ice storage. We've made a minor change to our program format this year. Rather than host a live question and answer session, we'll provide answers to your emailed or faxed in questions. Your event coordinator will distribute the answers, so please fax in your questions during the broadcast to the number on your screen or email enl@trane.com. Be sure to provide your email address so we can respond directly to you. All answers will be posted in a few weeks, so be sure to follow up with your Trane sales office for a copy. To cover this information today, we're delighted to have as our guest Paul Valenta. Paul is a marketing and sales manager at CalMac Manufacturing Corporation with over 20 years' experience in the ice energy field. Also joining us today is Susanna Hansen. Susanna is an applications engineer and certified energy manager. Her expertise includes ice storage, chilled water systems, and ASHRAE Standard 90.1. And a familiar face to most of you is Lee Klein. Lee is a systems engineer whose primary responsibility is to help customers with the design and application of HVAC systems in buildings. As always, we have a lot of information to cover today. So Lee, would you get us started by answering the question, why the resurgence in ice storage and why now?
I'll give it a shot. We believe the real answers are because your customers need it, and for a number of reasons, now is the time. Let me give you 3 of the numerous reasons. 1, green power needs it. 2, it reduces CO2 emissions. And 3, it saves money and has a good ROI. Let's talk about why green power needs it. What is this? Alert observers would say bituminous coal, or if you're radically green, you might say it's one of those evil fossil fuels. And what's this? A barrel of crude oil. With last summer's oil prices, this is about the size of barrel that I could afford. But more importantly, these are stored energy. Energy that can be used when it's needed and held on to when it's not. That is a very valuable characteristic of fossil fuels that most green power, wind and solar, inherently lack. That deficiency is something that is currently the subject of a fair amount of research and debate. To understand why storage is important, it's helpful to look at data from 2 different forms of green power. These charts are from a Carnegie Mellon Electricity Institute study. They show the power spectrum of wind energy generation over a 10-day period and solar power generation over a 12-hour daylight period. Notice that in both cases, on a daily basis and on an hourly basis, the energy produced varies greatly and is not a function of the load requirement. These charts are examples of why utility companies call wind and solar energy non-dispatchable. Their output cannot be controlled to meet the actual load requirement as the utility's conventional forms of generation can be. This does not make green power bad, nor would I suggest that it should prevent its growth. But it does mean we need to learn new ways of energy control and storage to maximize its usefulness. In a little while, we will discuss building and utility load factors, which have an impact on the use of green power as well. What about the second point? Thermal storage reduces the emissions of CO2 and other byproducts of conventional power generation. The best study I could find on this is the ASHRAE TC 6.9 research project, which is a simulation of source energy utilization and emissions for HVAC systems by the University of Wisconsin-Madison. The researchers in this study compared two different building types, an office building and a high school. And they modeled the buildings as served by two different model utilities using different mixes of source energy. One utility using primarily coal to generate power, and one with a more balanced generation portfolio of coal and natural gas. The data in this table, summarized from the ASHRAE report, shows the impact on site energy, source energy, and CO2 emissions for a standard chilled water system versus a partial storage system. In every case, the ice storage system not only lowered the site electrical usage, that is kWh, but the source energy usage and overall CO2 emissions by 12 to 14%. For two full storage ice simulations, not shown here, the reductions were typically in the range of 3 to 7%. The conclusions of the 99 TRP study were, and I quote, "Thermal energy storage systems should be promoted as an environmentally beneficial technology. These systems have historically been touted as beneficial in terms of operation cost. This study suggests that the economic benefits can be accompanied by environmental ones." And it goes on to say, source energy reductions were generally on the order of 10%. Global warming reductions were also on the order of 10%. My third proposition is that thermal storage saves money and has a good ROI. I'm going to leave the real proof of this to Susanna in the economic analysis section of this ENL. Now, there are some mistakes that can prevent these benefits from happening. Throughout the rest of this broadcast, we'll work to help you see how to prevent these and get the most out of a thermal storage system. One final comment in this Why Thermal Storage section. In the introduction, Jeannie told you this broadcast was going to be focused on ice energy storage. You may be asking, why not chilled water storage? It is absolutely driven by market applicability. Because of the storage volume requirements, ice energy storage is most often supplied using prefabricated modular tanks. This has the impact of providing a relatively low and linear installed cost per ton-hour of storage over a wide capacity range, as depicted in this chart. This helps make ice economically feasible for many building types. Chilled water energy storage is typically installed using large volume, site-erected tanks. The cost per ton-hour for such tanks starts out high, but decreases as the volume of storage increases. The installed cost crossover point is very job dependent, but a rule of thumb is that chilled water starts becoming cost competitive with ice at around 10,000 ton-hours. There are two distinct advantages that chilled water storage has versus other technologies. One, that it can be very rapidly discharged. It takes a few hours to discharge an ice system, while a chilled water system can be discharged as fast as you can pump the tank. Secondly, in the case of an emergency, the stored water can be used for other purposes, such as fire suppression or as cooling tower makeup water. Insurance companies may give rate discounts for such secondary uses. but we see ice being deployed for everything from church buildings with 25 ton-hours of storage all the way up to 29,000 ton-hours on the JCPenney headquarters in Dallas, Texas. So because of the much wider market applicability, the rest of this E&L will focus on ice energy storage. Now, let's take a closer look at the dominant form of ice storage, internal melt ice on pipe. Paul, would you take us through that?
I'd be glad to, Lee. Manufacturers offer a variety of technologies to the marketplace as no technology applies to every application. Ice storage commercial system offerings include ice harvester systems, ice on pipe external melt systems, encapsulated systems, a slurry system, and the most popular, ice on pipe internal melt. Today we'll focus on the ice on pipe internal melt technology. For information on the other types of systems and where they are applicable, please review Trane's AC Clinic on energy storage. Before we examine ice on pipe internal melt technology, we must understand today's ice energy storage systems for comfort cooling applications must be capable of providing 6 modes of operation. These 6 modes may not be used on each and every project, but having the ability to change modes is an important aspect of flexible energy storage design. The 6 modes are charging with a nighttime load, cooling with chiller only, cooling with ice only, cooling with chiller and ice, and don't forget off. Understanding these requirements helps one understand how ice on pipe internal melt came to be the market leader for comfort cooling projects. So keep these modes of operation in mind as we proceed. So why are ice on pipe internal melt systems so popular? It's because they provide all 6 modes, which in turn provide operation flexibility for the building operator, and they easily adapt to traditional chilled water systems, making the design process familiar. Additionally, internal melt systems have a managed flow path, so performance data is cataloged, and factory assembly assures consistent quality and long-term operational success. Internal melt systems also adapt easily to existing or new projects, both large and small. These modular systems offer fast and simple installation to help keep first costs low and have been shown to be more efficient and reliable than other ice storage technologies in comfort cooling applications. There are many internal melt systems that have operated for 20 years or longer. The other ice storage technologies that I mentioned are not easily configured to provide the most viable design strategy, partial storage, and they tend to be custom designs which add design and installation complexity, increasing first costs. No systems are perfect, and internal melt systems are no different. Secondary heat transfer fluids are necessary, and because of the modular concept, direct burial is not as simple as digging a hole. Let's take a closer look to get a better understanding of internal melt systems. I think you'll agree using internal melt technology is really just an extension of a chilled water system. A typical system of chilled water looks more or less like what is shown here, and we know how to design these systems really well. In the old days, the chilled water system would have to be adapted to accept the ice storage system. Instead, internal melt energy storage systems are conventional chilled water systems with a few extra simple components. The simplest storage design requires adding a blending valve, a diverting valve, an ice tank farm, some extra controls, and heat transfer fluid to a conventional chilled water system. In the ice making mode, cold glycol produced by the chiller is circulated through the heat exchanger inside the tank. The heat exchanger is surrounded by static water. Ice begins to form around the tubes during the charging process. After some time, the ice gets thicker and thicker until a complete charge is made and the area around the entire heat exchanger is frozen. During the day, warm glycol returns from the load and passes through the ice tank tubes. Ice begins melting from the inside out as the load is absorbed by the stored cooling. The ice closest to the tubes is the most efficient to make, and it's the first used. The more expensive ice furthest from the coils remains in the tank until it is needed. When the tank recharges, ice can begin forming immediately. Ice does not have to be made through ice, as is the case with ice-on-coil external melt systems. This improves efficiency and eliminates the need to predict ice consumption for efficient operation. Some rules of thumb have been developed for internal melt designs that can serve as the compass to get the design moving in the right direction. Most projects are designed with partial storage strategies. This tends to be the best use of assets. Full storage systems are installed typically where supported by specific rates and rebates. Chillers have less capacity in the ice-making mode. A good rule of thumb is ice-making capacity is about 65% of nominal. So a 100-ton chiller at nominal conditions will provide 65 ice-making tons. Susanna will talk about efficiency differences later in the broadcast. Ice-making time is usually about 8 to 10 hours, sometimes more and sometimes less. If possible, leave an unscheduled chiller hour or two for flexibility. Next, typical partial storage systems store about a quarter to a third of the total design day ton hours, and the chillers downsized about 35% and a little more in schools. And finally, wherever possible, use efficient chilled water or glycol distribution systems by using delta T's in the 15 to 18 degree range to minimize flow to the downsized equipment and to save energy. Now that we understand the basics and some rules of thumb regarding internal melt energy storage systems, Susanna is going to drill down in the design process.
Thanks, Paul. To visualize the energy that we're considering shifting and storing, consider the following load duration curve of the hourly building and HVAC kW. The shape of the curve as you go towards the left shows you how many hours drive the peak demand. It's clear that HVAC is the reason for the tremendous variation in kW. From this, we can also infer something about the cooling diversity factor. This is the average load divided by the peak load. You can either look at it from the utility's perspective in kW or from the chiller's perspective. In this K through 12 school, the pre-thermal storage diversity factor was 16%. Said another way, the peak is over 6 times the average. Any improvement we can make to the average kW of the chiller will improve the kW diversity factor, which is what utilities encourage through rate structures and incentives. If there's on-site power generation, a flat load duration curve makes power generation much more economical. For an example, we turn to a familiar installation. The University of Arizona is a great success story on many fronts, and their ice storage system is no exception. The U of A uses on-site power generation, so they are fully aware of the importance of having nighttime electricity consumers. By making ice at night, there's a much more constant loading of the power generation equipment. This drives down their cost per kilowatt and creates heat recovery for their steam plant. 23,000 ton hours create over $400,000 of savings per year. As an added bonus, their now flat load profile helps during their utility rate negotiations. But for design purposes, the shape of the load duration curve can't tell us how much ice and which chiller size we need on a design day. For that, we need to shift our focus to the cooling load profile. Here's a simple load profile for an office building with a design day peak load of 600 tons. There are no unoccupied cooling loads in this case for simplicity of illustration. Next, we'll overlay a conventional system size for this profile. It's common for the chiller or chillers to be 20 to 30% oversized from peak load for a safety factor and redundancy. One strategy is add 20% to the peak load and divide by 3. For a 600-ton load, that's 3 240-ton chillers. The blue columns show each hour's available capacity, and there's certainly a lot of excess. The chillers are off more than they're on, even on the hottest day of the year. So you can imagine a milder day. And all of those chillers must be maintained so they can operate at a moment's notice. Now compare the load profile to the cooling available with partial storage. An equivalent partial storage system in this case could be 2 240-ton chillers and just over 2,000 ton-hours of ice storage. The storage system has spare capacity too on a design day. One of the hidden or overlooked benefits of ice storage is what I'm going to call useful redundancy. Even though the chiller capacity is 30% smaller than the peak load, the storage provides the safety factor and the redundancy. If we overlay the conventional 3 chiller system's capacity, we find that the storage system has more cooling available during the critical peak hours. One myth is that ice storage systems have less redundancy. Let's look at what happens during an equipment failure. If you have 3 chillers and one's unavailable, or if ice is unavailable, you'll be short cooling in 6 of 11 hours, shown in red. If a chiller is down but you have storage available, the remaining chiller and storage would be short capacity for only 4 of 11 hours. Or you could use the ice more slowly and have a similar situation to an offline chiller. For true N+1 redundancy, both systems would need 300-ton chillers, 3 for the conventional and 2 for the partial storage system. Any off-peak cooling system can meet the same redundancy criteria as a conventional system at a comparable cost. When rebates were plentiful, full storage was more common. Full storage is when the chiller doesn't operate at all during the on-peak electricity window. But if the on-peak window is short enough, and we've seen some that are only 2 to 4 hours long, more hours are available for charging the required number of tanks. In these cases, it can be economical to do full storage, provided the discharge rate is fast enough. Partial storage is much more common, and it targets either on-peak reduction or load shifting to cheaper or more efficient cooling hours. Partial storage avoids about half of the chiller demand for a much smaller initial investment in most cases. For today's broadcast, we'll go through the process of designing a small, air-cooled chiller with internal melt ice storage system. We're making this choice so that we can drill down to a deeper level of detail and get as specific as we can, while still addressing issues that virtually all ice storage projects face. Air-cooled systems have a lower initial investment, and they can offer the efficiency of a centrifugal chiller without ice storage. Water-cooled chillers can be larger for economies of scale on larger projects. But from an ice storage design perspective, air-cooled and water-cooled systems are about the same. So all the elements we'll be describing today will also apply to water-cooled systems. There'll just be a little less selecting to do since we won't have a condenser pump and cooling tower. Speaking of cooling towers, here's one benefit that goes unnoticed in water-cooled systems. While we design the system to handle the design day, there will be many cooler days when ice can do even more. Water economizing cycles often can't meet the load with just the economizer. If the ice were in series and downstream of the economizer, we get the benefits of the chiller working against a cooler condition at night. Cold tower water is not free, and ice provides another level of flexibility for minimizing system energy. The other difference between air-cooled and water-cooled is that air-cooled shows a better efficiency benefit from ice storage. This is because during nighttime ice making mode, the ambient dry bulb drops more significantly than the ambient wet bulb. This graph shows the difference between design ambient temperatures, both dry bulb and wet bulb, and the typical daily August temperatures in Memphis. Note that the ambient relief for dry bulb is always more than the ambient relief of wet bulb. This difference in condenser relief is key to dispelling the myth that air-cooled ice systems perform inefficiently during the ice build mode. An air-cooled chiller can make ice at night with better efficiency than that same air-cooled chiller makes chilled water during a design day. This next slide shows that an air-cooled chiller in ice-making mode still has a slightly higher EER than the same chiller on a design day making 45 or even 50-degree solution. This is due to the condenser ambient relief from 95-degree daytime temperatures to 75-degree nighttime temperatures when the ice is being made. But EER doesn't tell the whole story because it doesn't factor in the smaller size of the chiller in an ice storage system or the longer run hours of the ice storage chiller. We have to go to kW to find out what we'll be setting our on-peak demand charge and to kilowatt hours to compare actual energy use. Just how much smaller could the chiller be? Fossil Ridge High School is a phenomenal example of designing for a small peak load and a small chiller. Because of the many structural and other design elements, prior to ice storage, this large high school's peak load was just over 1,000 square feet per ton. Now, you may recall that our ingrained rule of thumb is 400 square feet per ton, so that is really remarkable. Once they added ice storage, the installed chiller capacity was a whopping 2,000 square feet per ton. This is one reason why Fossil Ridge won the first place award in the ASHRAE institutional category in 2008. While Fossil Ridge was a brand new school, chiller replacements are a window of opportunity for adding ice storage. Ice chillers are no more expensive than standard cooling chillers, but many chillers do have to be selected to be suitable for it. The total cost of the chillers can be less if they're downsized. And it's not hard to start thinking about an ice retrofit when energy prices are high or interruptions are common. Incentives are also available in both the public and private sectors. Okay, so let's now talk about conceptualizing the system and how ice might be incorporated into a chilled water system. Here we have the storage tanks located downstream of the chiller. The chiller receives the warmest entering fluid temperature and produces a higher leaving fluid temperature. This gives us increased chiller capacity and improved efficiency. That's great for screw chillers, which are more sensitive to making colder water than centrifugals. This example shows an air-cooled chiller with ice downstream and one pump. The system's quite simple, but it has limitations. Night cooling loads while the tanks are being charged will have to use the cold charge mode chilled fluid temperatures. If we add an extra pump and a tempering valve, V2, we can adjust the temperature of the fluid sent to the air handlers during charge plus cool mode. The back pressure regulating valve prevents fluid from migrating into the system during the charge mode when P2 is not operating. Larger systems using centrifugal chillers will see a bigger cost advantage with the ice upstream of the chiller. More storage capacity is available from the tanks if the tank leaving temperature is higher. As the storage 10 hours increase on larger and larger systems, the cost advantage grows because this added capacity starts to avoid the need for several tanks. And centrifugal chillers are quite comfortable making cold water, especially centrifugals that have been optimized for making ice. There are competing benefits of upstream and downstream. Here's a summary of the rationale for whether to put the ice upstream or downstream of the chiller. Small systems with helical rotary or scroll chillers locate the tanks downstream of the chillers. But in large systems that use centrifugal chillers, locate the tanks upstream. It's easy if you just remember SIC. Screw a scroll, then ice, then centrifugal. Before we go further, how do we know if ice is right for our project? Lee, can you walk us through that?
There are a number of things to consider during the design process. Most are obvious, but the importance of a few cannot be overstated. Since we're talking process, it's only appropriate to have a process diagram. Shown here is a process diagram for qualifying a job. Later we'll have a similar one for the detailed design phase. From a qualifying perspective, we are going to be looking for a job with certain characteristics. A chilled water-based system is fundamental. For some people who might be considering a DX system but would prefer chilled water, the additional operating cost advantage that ice storage brings can be the key to justifying that desire. Secondly, it's important that the owner plans to spend money on some type of installation. It may be a new building or a chiller changeout. The point is that it makes sense to consider ice storage as an alternate to doing something else, so you have an ROI comparison basis. Having building off time, or at least reduced loads at night, as well as a place to site the ice tanks is also very important. Finally, many owners would prefer air-cooled chillers, but local or state codes may limit the allowed system capacity. Some codes, such as California Title 24, have an exception for systems with energy storage. Or the addition of ice will allow the same capacity chillers to serve a much higher peak load. There are many other building operational issues that can have an impact on the value of an ice energy storage system. For example, the fact that you can get cooling by only running the pumps can have a significant impact on backup generator sizing. More and more building owners want to strut their greenness, and schools want to use their buildings as teaching tools. Integrating the ice storage benefits into these efforts can increase the soft benefits of the system. It only makes sense to take advantage of every possible benefit. One thing that we have seen become a roadblock to adding ice to an HVAC system is tank location. But from what we saw on recent jobs, when the economics work, there's not a better example of where there's a will, there's a way. With a little creativity, it's amazing where ice storage tanks can be located. Susanna will discuss the distribution system considerations a little later. However, one thing to consider for any system with storage is that it's very worthwhile to explore taking advantage of the extended chilled water temperatures that are available and design the system with low supply water temperatures and lower flows. The two biggest mistakes we see people making during the qualification process are failing to get a good design day load curve and assuming a blended electrical billing rate. You cannot achieve proper ice storage design and financial justification without a reasonably accurate building load curve. It has such a huge influence on the design of the system. It's important to understand not only the peak load value, but the shape of the facility load curve as well. Load curves for new buildings will obviously have to be acquired from a load analysis program. While existing buildings can be modeled that way as well, if chiller or BAS system logs are available, they can serve as good load information sources also. Paul, would you take us through a couple different analysis tools to help us show why load data is so important?
Lee, your comments are right on the money. We need the cooling load profile so we can select the ice storage system equipment to be used in the design and ultimately to perform the economic analysis. As Lee mentioned, the load profile can be obtained using a building load analysis program or operating logs and utility bills for an existing building. Nighttime loads are an important part of an ice storage system design, and proper care must be used to include nighttime loads in the equipment selection process. A rule of thumb states that if nighttime loads are 20% or less of design peak, the cooling requirement can be met with the ice-making chiller. If the nighttime load is greater than 20% of peak, the designer should consider using a separate dedicated nighttime chiller. Internal melt storage performance is not only dependent on flow rates and temperatures, but also on the amount of remaining ice. As loads vary throughout the design day and the ice inventory is gradually depleted, designers have to ensure that the chiller and storage equipment can provide adequate cooling capacity for all conditions. Manual selections are tedious, but computer selection programs make this necessary design step easy. In addition to the load profile information, the typical selection program will need the following information: the heat transfer fluid, type and the concentration, a tank model to be selected, the amount the chiller can contribute during the day, the chiller ice-making capacity, and the system supply and return temperatures, or the delta T, along with the defined hours of full and partial storage. Let's select equipment for the small school. For this discussion, we will use 25% EG for our heat transfer fluid. The selection will be based upon the ice tank model 1190. Next, input the chiller's daytime cooling contribution as a percentage of nominal. Let's use 100%. Then input the chiller ice-making capacity as a percent of nominal, about 70% in this case. Then input the system supply and return temperatures of 40 and 56, and in this case, the chiller is upstream of the ice. Next, input the load profile in tons, along with the ton hours of ice-making and discharging. Over the weekend and nights, the BAS system allows the building temperature to drift up. The next day, the temperature is ramped down by the automation controls in order to have the building reach set point temperature by class time. This causes the high Monday morning startup loads of our peak August day. The hour type is denoted by I for ice making, or P for partial storage cooling, or F for a full storage hour. The chiller percentage entries are automatically populated from the previous input screen and represent the chiller capacity as a percent of nominal for daytime contribution and ice making. Click the next arrow and the program does its initial calculation of the minimum selection. Here is the preliminary selection output screen. With the criteria we input, the initial selection requires a nominal 46-ton ice chiller that provides 32 tons of capacity at ice making and 3 ice tanks.
So Paul, what is this initial selection giving us?
This is the smallest energy storage system that can meet the load on the design day. This system leaves very little room for error in loads or operation on a design day, and it really leaves very little room for growth.
But the chiller is significantly downsized from what it would be in a conventional chiller-only system, from 80 tons down to 46 tons. That will save us money on the cost of the chiller that we can then use to buy the ice storage tanks. Paul, would you say this is typically the best initial chiller and tank selection for a job?
Typically not, because the minimum equipment required provides no safety factor, and the system is not using much of the third ice tank. This may not be the best first or life cycle cost option.
Can you show us this in the IcePick program?
Sure. First, let's look at what happens if we input an actual chiller selection. Then we'll follow that up with increasing the chiller to the next cataloged size. The closest chiller to the minimum capacity required is a nominal 52-ton machine. The chiller catalog reveals that it provides 48 tons at 95-degree ambient during the day and generates about 34 tons of ice each hour at night in 80-degree ambient temperatures. Let's input that data into the Select New Chiller box within the program and see what happens. This larger chiller provides a range of tanks. For this project, the tank range is not big, but the results demonstrate how the larger chiller can contribute more in both day and night modes. In the day mode, the chiller can take a larger portion of the cooling load, thus less capacity is required from the ice, so the minimum number of tanks is 1.9. Conversely, the larger chiller can charge more tanks at night, increasing the maximum number of tanks to 2.3. So the ice can take a larger portion of the cooling load and allow the chiller to run at reduced loads during the day. The next larger size in the catalog is a nominal 60-ton chiller, and it provides 58 tons. So let's see what happens in IcePick during the design day analysis if the nominal 58-ton chiller is selected. As you would expect with a larger chiller, the minimum number of tanks is lower and the maximum is larger. On a day when charging begins with empty tanks and using the time available, the third tank is filled up to 70%. If we choose to invest in 3 tanks, energy savings will be increased by demand limiting the chiller operation during the day. If lower first costs are desired, the 2-tank option will work, and it can complete a charge in less time, providing operational flexibility. That does not preclude a 3rd tank from being added in the future.
Paul, it seems that so far we've been concentrating on the peak load tons for chiller and tank sizing. How does the full design day load curve come into play?
It's a good question. Once the program provides an initial selection, it must be validated in the design day analysis section of the IcePick program. The validation is required because thermal storage performance is also dependent on the amount of remaining ice. The full design day analysis confirms the selection by performing hour-by-hour energy calculations and comparing the results with the tank performance model. As loads vary throughout the design day, the ice inventory is gradually depleted. The program models the selection to see if the chiller and storage equipment can provide adequate cooling capacity for all conditions. If it's not valid, flags will appear and the process must be repeated with more storage until a valid selection is made. The output of this section has a lot of useful information for the designer as well. Let's look at some. Notice hours 4 and 5 show the chiller is unscheduled as there is no load and it's not charging. That provides scheduling flexibility. Notice hour 8 shows a peak load of 77 tons with the load split. The chiller provides 48 tons and 29 tons coming from the 2 ice tanks. This is about a 60-40 chiller-ice split, which is common. Ice Pick also provides a variety of other design information, such as pressure drops, inventory, and charging temperatures. As you can see, there are options to consider. The minimal selection was a 46-ton chiller with 3 ice tanks. It is most likely not the cheapest first cost and does not provide much flexibility for unscheduled loads or expansion. The best choice is likely the 60-ton chiller and 2 ice tanks. Using the larger chiller eliminates the 3rd tank, reducing first cost. It provides an hour of scheduling flexibility, and the safety factor is improved because the chiller is demand limited on a peak day. So if there are temporary unexpected loads, the controls can remove the demand limit to get 10 more tons. The larger chiller also provides the ability to charge another tank in the future. Would an even larger 70-ton chiller with 3 tanks be a better choice? Later, Susanna will include this in a rigorous economic analysis to see if our choices are best for this design. Lee, what else did you want to say about the design process?
As you well know, Paul, the available utility rates and modeling them properly is also critical to the qualification of any storage system. Particularly important is breaking out the demand charges and time of day or stepped rate structures. Modeling with a blended rate is a sure way to badly underestimate a storage system's savings potential. Electrical rates can be very complex today because of demand and cost pressures. But electrical rates are also complicated because setting rates is a political process. So rates come in many different shapes and sizes. The rates, in whatever shape they come, tend to reward consumers with higher load factors. For some rates, utilities even look at a building's monthly load factor to set its rate for the next year. A monthly load factor is defined as the month's actual kWh consumption divided by the peak demand times the number of hours in the month. Utilities design rates that reward high load factors, consumption that is more even 24 hours a day. They penalize low load factors, that is peaky consumption. Office buildings' load factors tend to range from 0.35 to 0.52, and schools are usually lower because their days are shorter. Paul, this is very important to your business. How do load factors relate to utility rates?
They sure do, Lee, and here's why. Almost all utilities have essentially a half-off sale at night in some form or fashion to encourage higher load factors. Sometimes owners or designers have to dig to find the half-off sale, which is used to evaluate the load factor improvement provided by energy storage. The first rate to look at is the most common, a simple demand rate. They tend to vary. Some might have a time of day energy price, but most don't. A common myth about ICE energy storage is that time of day rates with low nighttime kilowatt hour charges are needed to make the economics work. That's not the case. Most of the ICE storage projects do not have time of day rates. Air-conditioned buildings peak during the heat of day, largely due to HVAC equipment. Since demand charges are typically 60% of the electric bill, significant savings are available by shifting cooling load. Any savings that come from lower nighttime time of day costs are a welcome bonus. Let's compare cooling costs on a standard rate. At night, cooling is made with an air-cooled chiller and stored. During the day, it is made directly with an air-cooled chiller. In this example, daytime peaking building has an $11 per kilowatt demand charge and an 8-cent per kilowatt hour energy charge and a load factor of 30%. Each kilowatt hour costs 8 cents, day or night. If the cooling is made at night, there is no demand contribution to the cooling costs. If cooling is made during the day, contributing to the peak demand, it will add about 6 cents to each kilowatt hour. So how much does a ton-hour of cooling cost? During the night, the cost will be just over 10 cents per ton-hour. During the day, a ton-hour costs almost 19 cents, a half-price sale with standard no time of day rates. Stepped rates can also be good for storage. They can be tricky to evaluate because we tend to look at them like a typical demand rate. Most times, the published demand charge in a stepped rate cannot be thought of or compared to a demand charge in a conventional rate. The actual, or as I call it, the effective demand charge, is not obvious. For example, a stepped rate in Georgia has a published demand charge of $6.83 per kilowatt. Is it really? Let's look at a typical stepped rate and see if we can determine why stepped rates penalize low load factors. Here is an example of a published stepped rate from Georgia Power I found on the internet. There are 3 hidden gotchas in determining the bill that stick out. The energy charges change in steps. In utility rate terms, typical buildings have between 300 and 400 hours of kilowatt hour per peak kilowatt usage per month. Many buildings can never even reach the lower cost steps without improved load factor. Second, there is a 95% ratchet charge based upon the summer peak demand, and demand plays a significant role in determining energy charges. Needless to say, this rate is load factor sensitive. The utility itself says its effective demand is between $12 and $14 per kilowatt. Flat and real-time pricing rates are more difficult to use in life cycle analysis because energy costs are not published and are difficult, if not impossible, to predict. With higher risk comes more savings, so energy storage customers who do their homework of understanding the rates and how they change with load factor, or take a leap of faith, can see significant savings. Some projects are economically justified using simpler rates, but switch to real-time pricing or even flat rates after a high load factor consumption history has been established. Today's rates have many structures and they all encourage using off-peak electricity. Lee?
While working through all these technical issues is important, it's also important not to forget the goal of the qualification process. That is to create a legitimate and compelling financial proposition. What I learned during a recent trip to New York is that if you can show the financial benefit, every other issue seems to magically disappear. A key point to make in the justification of an ICE energy storage system is that for a reasonable payback, don't add too much ice. That is the #1 mistake that system designers make that causes the system financials not to work. Once the system is qualified and the proposal accepted, you'll find that the detailed design phase is really just a refining iteration on the qualifying step to tighten the chiller selections and further document the design. This is also when the very important control sequence of operation is developed. We'll talk more about that also in a little while. Let's move on. Susanna, would you take us through some important design details?
Thanks, Lee. In his selection, Paul used 25% ethylene glycol in ice pick. Properly using glycol is a key point. Let's explore the effect of glycol on the components in the system and how we might compensate for the energy penalties. Propylene glycol has a substantially higher viscosity than ethylene glycol, and both are higher than water. A system using either type of glycol will require larger pumps and potentially larger cooling coils from lost heat transfer. But the properties of propylene glycol are further from water. For most ice storage systems, the preferred heat transfer fluid is 25% ethylene glycol and 75% water. It provides sufficient freeze protection and minimizes the negative impact on heat transfer in the other system components. Ethylene glycol is a stable fluid with a long life, non-corrosive, and safe for coils, pipes, and chiller components when properly inhibited. We see propylene glycol used primarily in food processing or pharmaceuticals. System designs cannot substitute PG for EG without re-engineering the other components of the system. Knowing the downsides of glycol, we should ask ourselves, how much of the system will have glycol in it? In smaller systems, glycol everywhere lets us avoid the heat exchanger and frost protection in air handlers. On larger systems, the cost of having glycol throughout the system gets more expensive. Pumping energy is more pronounced than in a smaller system. More glycol-compatible control valves have ongoing additional maintenance, but a heat exchanger in a closed system requires very little maintenance, and its cost is a small portion of the system installed cost. If the system exceeds the pressure limit of 90 psi on the tank, a heat exchanger may be needed anyway. Next, we ask ourselves, if we do have glycol in the coils, can we overcome the energy impact? Let's quantify that penalty. What happens to cooling coil performance? When we add ethylene glycol, cooling capacity drops 13% and pressure drop increases 14%. Both performance losses are caused by the lower specific heat and higher viscosity. Several options are available to recover lost capacity through coil selection and system design. If this coil is being selected for a new installation, one way to get the desired capacity is to increase the surface area. Going from 6 to 8 rows returns the capacity of the coil. This approach increases the air and fluid pressure drops. Another thing we can do is increase the flow rate. This avoids any increase in air pressure drop, but results in an even higher fluid pressure drop and pump energy than the previous choice. Typically, the best approach for getting the capacity back is to decrease the coil entering temperature from 45 to 40. This option has no impact on the air side and a lower fluid flow rate than the previous 3 options. Reducing the entering fluid temperature has proven to be the least expensive in terms of both installed cost and energy cost. And this approach applies to both new installations and retrofit situations. Reducing the entering fluid temperature even further to 38 degrees provides further benefits. The improvement in heat transfer performance gives us an even lower flow rate and a lower fluid pressure drop than the original coil selection based on water. This results in less pump power than the system that did not contain glycol. Remember, we're talking about the same coil here. Alternatively, the coil given 38-degree fluid could be reselected with fewer fins and the original flow rate. This would decrease the cost of the coil and give us a lower air pressure drop. Finally, a cold entering fluid temperature creates the opportunity to reduce the supply air temperature. Cold air systems can allow some combination of smaller air handlers, smaller VAV terminals, and smaller ducts, and/or reduce supply fan energy use. Producing a colder fluid temperature, however, makes the chiller work harder and use more energy. The key is to strike a balance between all the system components. In existing systems, we can avoid pumping glycol everywhere by installing a heat exchanger between the existing chilled water system and the new ice storage system. Now the antifreeze and water solution is only circulated through the new system components. This approach has the added benefit of shielding the ice storage tanks from higher head pressures that may be generated by the existing pumping system, and we don't have to reselect the existing cooling-only chillers and system pumps for glycol. We can even have an air-cooled chiller in the ice plant. You may have noticed that the heat exchanger here is located in series with one of the existing chillers, but in parallel with the other. This allows the heat exchanger to be sized for only the portion of the cooling load that is to be satisfied by ice, not for the entire load, and this reduces the heat exchanger cost. But for more redundancy, this heat exchanger could be sized for the full flow of the chiller and the ice, for when the chiller in parallel is unavailable. Let's look at how Paul's ice pick tank selection lines up with the chiller selection. What we need to find out here is how the glycol affects the chillers, their capacity and efficiency in standard cooling and ice charging modes, and the minimum and maximum flow rates. We'll use these values later in the energy analysis. We'll start with the known temperatures and flows from ice pick. These were determined by the nominal chiller size, the hours and spare capacity available for charging, and the number of tanks. Here is our 60-ton chiller during discharge plus cool mode. We've got a 10.7 EER and we're making 48-degree water, which is halfway from 40 to 56. For modeling purposes, we don't need the part load value because this is handled with the unloading curves in Trace. In ice build mode, we're able to make 40 tons at 21 degrees, which is when there is 80-degree ambient. The pressure drop is about 29 feet. However, we must enter in Trace the efficiency of making 21-degree glycol at design ambient of 95 degrees. This is because the ambient modification curve will already improve the efficiency every hour that the ambient temperature is below design. We only needed this point to find out the capacity we'll experience over much of the charging mode. We would repeat this process for another pairing of chiller and tank. In our case, we also selected a 70-ton chiller matched up with 3 tanks. One thing to watch out for on the chiller and tank selection is the flow rate at the charging temperature. The limitations on operation will be different for different chiller types and potentially for different tank manufacturers. Work with the manufacturers to make sure the chiller and tank selections are appropriate for the desired system design. Whether we have glycol in them or not, the improved heat transfer performance of cooling coils leads us to a lower fluid temperature. If you've already got a chiller that makes cold fluid, why not take advantage of it? Another question that comes up a lot is, what system architecture should I use? All configurations are theoretically possible, but some will be much simpler than others. If you elect to vary the flow through the chillers, you'll have to consider new flow limitations as the temperatures change in the system between charging and discharging modes. Some of the commonly held positive and negative aspects of each system are amplified or minimized. But whatever architecture you select, the direction of flow during charge and discharge should be the same. That can be tricky in some designs, especially parallel designs. Because of the way the ice melts on the surface of the tubes, it's better to charge and discharge the tanks in the same direction. In constant volume systems with 3-way valves, ice can be beneficial if it allows for a wider system delta T. The pumping horsepower may be reduced enough to justify a larger constant volume system. But still, constant volume systems are probably best used in smaller existing systems. A lot of people have been asking us about variable primary flow in ice. We don't see as much advantage to variable primary flow as in many other systems. Frankly, variable primary flow just hasn't been done on enough ice jobs for us to comment on its successes or failures. We can go ahead and comment on the perceived benefits and drawbacks. The usual benefits still apply: reduced first cost, and from a control standpoint, if ice leads to a higher system delta T, the chiller has more flow turned down, which helps variable chiller flow work. We talked a lot about this in our September 2008 broadcast. If there is glycol in the system, variable primary flow can negate even more of the glycol pump penalties than the primary-secondary system, although a wide delta T may have eliminated the pump penalty already. Other potential issues are that IcePick does not model variable flow, but we believe the selections are probably conservative. Controls get more complicated as there are now more flow limits to manage for the different control modes. And finally, night cooling is more difficult because there is no longer a natural way to blend the water sent to the coils during charging mode. So condensation on piping, valves, and fittings must be addressed. The traditional decoupled system with a constant primary and a variable secondary loop is a very common system architecture. The decoupler simplifies pumping and control and serves as a natural way to blend water being sent to the coils during the charge and cool mode. If glycol is sent through the system, its impact on pump energy can be minimized by the variable flow through most of the system. With properly operating coils and valves and a modest amount of flow bypassing the coils, the return water temperature will be higher than with a constant flow system. This increases the net usable ton hours in upstream tanks. Although it's impossible to discuss every conceivable possibility, let's look at several fairly common and simplified circumstances. In the previous slides, we didn't talk much about the pumps. Let's bring back that primary-secondary design for a moment. Here's a system with ice storage tanks located downstream of the chiller. All modes of operation are easily accommodated. Primary loop delta T's must typically be at least 14 degrees. This lowers the flow to a level that is compatible with the reduced chiller and storage sizes. The storage tank operating pressure is reduced by placing the primary pump, P1, before the chiller. The modulating valve, V2, and bypass in the secondary loop provide added flexibility in the charge and discharge modes. P2 operates just like a regular distribution pump. The system doesn't change much with the chiller downstream. The only thing that changes is the colder temperature of the fluid going out to the coils during charge plus cool mode, because the chiller is downstream. V2 must blend fluid returned from the coils with fluid from the chiller in charge mode, which could be around 21 degrees. And notice this is a large design that requires glycol to the cooling coils. To avoid glycol to the cooling coils, we must put in a heat exchanger. So there will be another pump on the water side of the heat exchanger. But we must be careful to avoid creating conditions during the ice charging mode that could freeze the heat exchanger on the water side. Instead, we can put in another pump, raise the temperature of the glycol sent to the heat exchanger. This design is preferred because it avoids a heat exchanger freeze condition. Lee, is this a good time to talk about controls?
Sure. Controls. What's important to consider for controls on an internal melt ice energy storage system? We've chosen to break it down into these 4 areas. Let's first talk about defining and documenting the control modes. First, controls cannot achieve performance the system does not support. It is very important that the design supports all 6 operating modes. Paul mentioned these earlier, and they are shown on this slide. How can you know that the system will operate properly in each mode? The only way I can prove it to myself is to diagram out each mode with temperatures and flows and pressures so that you know where the water is supposed to flow and that it will actually flow there. Here's a diagram for our air-cooled energy storage system in the ice-making mode. As you can see, the ice valve is directing all the flow through the storage tanks. The controller can either take direct control of the valve position or trick it into this position by sending it a low, say 15-degree set point. The chiller is enabled in the ice mode with a set point lower than the design ice freeze set point to make sure the chiller fully loads. Since the average charge temperature is 22 degrees in our example, we'll send the chiller a 20-degree set point. The system operates in this mode until the tanks are fully charged. But how do we know when to terminate the freeze cycle? Fortunately, there's a reliable signal that is available to indicate the end of the freeze or charge mode. Because of the huge amount of heat transfer surface in the ice tanks, the temperature of the fluid leaving the ice tanks during the freeze cycle remains relatively constant until near charge completion. When almost all of the water is frozen, the ice in the tank begins to subcool and the temperature of the fluid leaving the tank begins to drop. This decrease in leaving fluid temperature can be used as an indicator of when the freeze mode is complete. This logic is so reliable and standardized it is built into many chiller control systems from the factory. The ice storage selection tools such as Ice Pick tell us the appropriate termination temperature based on the ice tank selection and the system design. While diagramming the system operation, it is extremely useful to document each component's operating conditions in a tabular form. This can be invaluable not only to the BAS technician, but when commissioning the system as well. Here is the mode that is sometimes overlooked: make ice and cool simultaneously. It's only different from the ice-making mode in that we turn on the distribution pump and send the blending valve the distribution supply 42-degree set point. If you remember from Susanna's design discussion, the main reason we've gone to this system configuration is to enable night cooling with normal cooling temperatures rather than the off ice tank temperature fluid. The key to the success of this mode of operation is the control of the blending valve, which means use a high-quality valve and see to it that it's commissioned properly. And now, the mode whose control is most critical. In this case, the system is cooling with a combination of chiller capacity, and ice melting. This could be called the partial storage mode. Think of this as a series chiller system. The upstream unit, the chiller, is controlled to take part of the load, and the downstream unit, the ice, picks up the rest. But in this case, rather than control the chiller to a chilled water set point, we control it by limiting its power draw with a demand limit signal. The downstream ice valve is given the desired system supply chilled water temperature and carries the balance of the load. There is one very neat feature of the system that we have here. Since we downsized the chiller in our design, it's actually impossible for this system to set a demand peak as high as a chiller-only system. So even if the chiller does not get demand limited perfectly, it will still save the owner operating cost. But what kind of demand limit signal should be given to the upstream chiller? The more the chiller is demand limited, the more ice will be used. The proper demand limit signal for the chiller depends on the amount of ice capacity designed into the system and the original energy goal for the system. So we need to understand this goal. Is it to peak shave the electrical kW demand cost, or is it to load shift the maximum daily kWh consumption? Let's look at each of these energy goals from a control implication point of view. If the goal is to peak shave, then it's critical to be able to control the rate of ice melt so that we do not run out of ice during the on-peak period. The worst thing that can happen is for the system to use up all the storage before the end of the on-peak billing period. If this were to happen, the chiller would have to load up and potentially set an on-peak demand. So at the end of the on-peak period, you want some ice left over. The system design software allows the designer to determine a chiller limit set point that safely shaves the greatest kW and still has some ice left over. Alternatively, if the goal is to load shift the maximum kWh consumption from on-peak to off-peak, then the system should melt as much ice as possible during the on-peak time period every day. In this case, we would limit the chiller to a lower load to push the load to the ice. The mode chart again reveals and reinforces the only difference in the operation of the system to meet these differing goals. It is the load limit signal given to the chiller. This is great news because it means that within the limits of the chiller and ice capacities, we can operate an ice system to meet either goal and easily change it in the future if utility rates change. The result of this exercise of creating these operational diagrams will be a completed mode table that looks something like this. If transition between modes is important, some designers add intermediate steps to let the control technicians know the proper sequence for a proper transition from one mode to another. This table becomes an important part of the job sequence. Before we leave this section on operating modes, it would be good to provide one comment on system diagnostics. Thermal storage systems have a number of extra blending or diverting valves, and the successful operation of the system depends on their proper operation. This tells me two things. Specify high-quality valves, don't accept cheap substitutes, and monitor their operation. You can monitor their operation with valve end switches or position potentiometers, or with system temperatures. For example, if the system is supposed to be in the ice-making mode, it's critical that all the chilled water should be going through the ice tanks. How could we tell if the ice valve was fully in the ice tank position? One easy way would be to compare the leaving tank temperature to the chiller return water temperature. If they are not the same, with a small allowance for pump heat, we know there is chilled water bypassing the tanks, and we should alarm the operator to that condition. We could do other similar system checks. The final step in engineering of the thermal storage control is the coordination of the modes of operation with the utility rate structure. This utility coordination can take a number of forms, but it typically evolves from the initial meeting with the electrical utility. The timing for mode control may be as simple as a fixed on-peak kW limit, or a time-of-day rate based on on-peak, off-peak schedules. It could, however, involve a sophisticated, internet-based real-time utility rate monitoring application. Real-time pricing could really make an ICE energy storage system dance. By this, I mean it will want to control the system to be real-time price responsive. With real-time pricing, the electrical utility can change the price they charge for electricity as often as every 15 minutes. The good news is that they give the building a 15-minute warning of a pending change in price. Based on that warning signal, the control system can easily change from an all-chiller cooling mode to an all-ice cooling mode, or even to a combined cooling and ice-making mode. A very nice feature of an internal melt energy storage system is that it is easy to seamlessly change operating modes to respond to such a signal. Once the mode timing or signaling is decided upon, it's typically a simple step to specify the responsibilities of the control company. There is one more element crucial to the success of any thermal storage system. That is, well-informed operators for the life of the system. As a matter of fact, when I asked our most experienced application engineer what might cause a failure of an ICE energy storage system, his first response was a second-generation operator. By that he meant one that was not well trained and familiar with the goals and operation of the system. The only way I know to combat this is to leave behind a well-documented system and a well-designed operator interface, one that informs and engages the operator with the system. In the past year, I've seen two innovative ways to accomplish this. The first is to specify that the controls vendor embed the same mode diagrams we've just been looking at into the operator interface. As the system switches from one mode to another, the system diagram in the control system changes to show the operator exactly what's happening. It really informs and engages the operator. The second innovative control method that's been shared makes it easy for the operator to be involved with the daily operation of the system and help optimize it on a daily basis. The operator is simply given 3 different buttons to push based on the expected load for the day or week. Choosing each button actually equates to choosing the demand limit set point for the chiller and therefore the ice melt rate. If the hot and humid day button is chosen, the chiller is allowed to load more so that the design day peak is shaved with ice. If the warm day button is chosen, then the chiller is limited more to cause the ice to shave the peak on milder days. On a cool day, the chiller may be stopped completely so the ice carries the full on-peak load. Of course, if the daily load unexpectedly rises, the system would override the operator's choice to make sure the building's cooling load is met, and of course inform the operator that it did so. We've discussed these 4 critical elements to the control of a storage system. With a little forethought, control of an ice storage system is actually quite easy, not much different from any other chiller plant control. My last comment would be that the importance of the design engineer's involvement in the commissioning of the system cannot be overstated. This cannot simply be left to the discretion of the control technician on the job. They can program anything that is desired. However, they seldom know what's needed. So I would urge you, proper commissioning is important with any building system, but possibly none more so than a thermal storage system. Well, we could go on with control details for a long time, but we need to move on to other important subjects. Paul, I think you have some installed cost comments to lead us into the economics section.
I do. First, cost is a big issue on some projects, and it's usually an indication that the storage system may be over-designed. If there's too big a difference in the first cost between conventional cooling and energy storage, there may be too much storage in the design. Make sure that the load profile being used does not have extra safety factor already included in the hour-by-hour numbers. Using the actual design day load data in a load profile allows the equipment to be selected as a system and lowers first cost. Another way to say it, and it's paradigm shifting, is to lower the chiller size by 20 to 40% and add storage for the safety factor needed on a design day. The benefit of this statement is that your safety factor is not a seldom used stranded asset. Instead, the safety factor is now a producer of lower operating costs every day. Use an efficient energy distribution system that has low flow and high delta T to minimize pipe and pump sizes. Low temperature air is a great way to reduce construction costs because these designs reduce fan size, fan horsepower, and duct sizes. Along with the smaller equipment comes smaller equipment rooms and plenums, which can save costs on the overall building envelope. Here's an example of a project for the state of Florida office building. The owner must have been from Missouri because he said, "Show me that ICE energy storage is cost competitive." So the engineer on the project designed it both ways. Plans and specs were issued for both designs, and the project was bid both ways. This data came from the actual bid documents and demonstrates that before rebates, the first cost of the ICE energy storage system was $56,000 less. Air distribution costs were essentially the same, and savings came from right-sizing the ICE energy storage system with smaller chillers and electrical equipment, and using an aggressive low-flow delta T chilled water distribution system. In your handouts, you'll find an ICE energy storage project data sheet. We created this to accompany this broadcast. We hope it will be helpful in reminding all of us the key design considerations. Let's move on and have Susanna get some of the details of the economics.
Thank you. We'll use TRACE for analyzing with our actual load profile and actual weather data. We picked a K-12 school in Memphis. It has humid evenings with a significant evening cooling load and a rate structure that doesn't appear very conducive to ICE storage. The standard GSA rate structure in Memphis is 9 cents per kilowatt hour for the first 15,000 and approximately 4.5 cents per kilowatt hour thereafter. Our demand charge is 0 for the first 50 kW and nearly $13 thereafter. This doesn't look like a good rate for ICE, but let's see if we can make it work without off-peak rates or a ratchet clause. Here's our building's load profile on a design day in August. Our peak is around 77 tons. We were careful to limit our nighttime loads by using a thermostat schedule that raised the space set points by as much as 4 degrees. In the morning, we made sure to start the system early, and we did this by adjusting the space set points back down slowly. In any case, our model will reflect the impact of this on our available ICE and energy consumed. For our base case, we added 20% to the peak load and divided by 2 to get 2 50-ton chillers. For our trace analysis, we'll take the 2 options that we identified in IcePick, a 60-ton air-cooled chiller with 320 ton-hours of ice storage in 2 tanks. We're also going to consider a 70-ton chiller with 3 tanks. All will use the primary-secondary system design. For the ice storage system, we'll use a 40 to 56 degree secondary cooling loop. So here are the results for the 60-ton chiller with 2 tanks. We did not get a rebate, so we should be representing a worst-case scenario for ICE. In this scenario, our annual savings come from having 1 less chiller and a reduced kW. Our energy costs were less for every month of the year. In this case, it's not about off-peak rates, it's about that $13 per kilowatt we're saving. Tanks are really easy to maintain, and the maintenance required for 1 fewer chiller is about $800 less annually. For the base case, we also have 1 more chiller to replace prior to the end of the 30-year study life. The analysis shows a payback of 3.5 years with an internal rate of return of 30%. Let's investigate the kW demand savings. Here we can see the impact our ICE had on the utility peak demand, which was set in August. Before ICE, our 2-chiller system needed the second chiller, and so its peak kW was 130 at 3 p.m. in August. After ICE, our peak happened a few hours earlier at the limit of the chiller, 70 kW. So a reduction of 60 kW. At $13 each, that's $780 per month. While a 30% return on investment is tough to beat, sometimes we find that the lowest first cost system does not offer the most attractive return on investment. A slightly larger system might have been more beneficial in the long term. What if we tried that 70-ton air-cooled chiller and 3 tanks? Here we can see that while a larger system is better than the no storage system, it's not better than the smaller storage system. While we were able to lower the peak kW even further to offset our additional first cost, we were not able to get the same amount of return on our investment. There's a $30,000 life cycle cost increase over the smaller system and modest savings over the no storage system. So our larger system does not pay back as well as the smaller system. But we did save more kW. Here are those details. We went from 70 kW down to 60 kW for the chillers, a reduction in building peak demand of 10 more kW. Let's go one step further and explore a what if. What if we could get a rebate for the storage system, either from the utility or from the state or from some other entity? Florida Power and Light provides $480 per shifted ton. Duke Power is at $200 per shifted kW. And New York is about $300 to $420 per shifted kW. Here we see our 3.7-year payback go to 0.7 years with the $200 per shifted kW rebate, like the one offered by Duke Power. Our smaller storage system shifted 60 kilowatts for a $12,000 rebate, and we got a $14,000 rebate on the larger system. That's an unbelievable 135% rate of return on that smaller system now. But still, the smaller system is the better choice, but only if we're confident that our utility won't penalize us all year for that extra 10 kW of peak demand in August, or give us incentives for off-peak cooling. If it did, the larger system starts to look more attractive and flexible with about a 4-year payback. Other overlooked savings include other capital investments that are avoided as a result of ice storage. For example, on a new building, we would have had smaller transformers and potentially less equipment room space. We didn't exploit cold air temperature systems and the resulting effects on those smaller air handlers, smaller ducts, etc. We kept these systems the same to reflect a retrofit worst-case situation. However, if there were going to be an expansion, our system could handle more square feet by using colder air. Be careful on your analysis of existing buildings, as you have to consider the system that's already installed and base the economics on the incremental cost. Make sure that you don't try to justify something that has to happen anyway. That is, you can't have a do-nothing base case. You have to be spending money anyway, whether it's a new system or a retrofit. And don't overlook negotiating with the utility for a different tariff. Jeannie?
Thanks, Susanna. Well, that brings us to the summary portion of today's presentation. Hopefully, we've provided you with enough information on ice energy storage systems. So let's recap what we've shown today. First, ice energy storage not only reduces a building's utility bill, it benefits the environment as well. Energy storage will play a significant role in the utility grid of the future. And ice energy storage is applicable over a wide range of building sizes and types. Adding ice storage to a chilled water system is simple and economical. And finally, for us, the biggest aha was that you don't need a time of day rate, an expensive kilowatt-hour charge, or even a demand ratchet to get an attractive 30% return on investment. Now, there are a number of publications available that provide more information on the material covered today, including several engineers' newsletters, an application manual, and numerous articles. A bibliography detailing these resources is available from your local site coordinator. Additionally, past broadcasts are available to order on Trane.com, so please check out the website for information on specific broadcasts. Please remember to fill out a survey and let us know how we're doing. And AIA members, please remember to turn in your member information to your local site coordinator. Now, we'll host one more Engineers Newsletter Live program this year. In November, Dennis Stanke and John Murphy will present various design strategies and technologies that can be used in air handling systems to reduce energy use and improve indoor air quality. So mark your calendars. Thanks for joining us today and have a great summer. We look forward to seeing you in the fall.